it's visible.
Wonderful. All right. So this talk is called Kernel Bug Horror Stories. It is a little collection of war stories from the last, I don't know, 15, 20 years of me at SUSE, um, which were interesting, potentially having large consequences. So as just a taster of what life at SUSE is like, and how SUSE's products are important for the world. So let me dive in. The first story is about the confusing consequences of planetary plasticity. It's called the leap second. And let me dive into a little bit of physics first, because that is actually required for the story to make any sense. Um, the Earth is squishy. The ball that we live on is more a tennis ball than a golf ball, in that actually other celestial bodies and their gravity are influencing it quite a bit in terms of changing its shape. And because the shape is changing as the Earth is turning around, causing tide, among others, but actually also deforming as the whole planet, that creates internal energy losses, right? And so the Earth is turning, and from that point of view, the sun and the moon are actually kind of stationary. And so that deformation is going through the Earth and is losing energy, and that means that a part of that energy is given back to the moon, to the sun, and the Earth is slowing down in its rotation. That didn't pose any problem in the past, because the measurements of the celestial movements were not precise enough for anybody to notice. But with the introduction of atomic clocks like the cesium clocks or rubidium, or actually hydrogen maser clocks, this is now very detectable, and we can actually notice that our clocks get out of whack with the position of the sun and the stars on the sky, which it would be a problem, because we actually want the sun to be at the top of the sky at noon. Um, but this is not as easy. This is not just slowing down. Actually, if we knew the exact rate at which the Earth is slowing down its rotation, we could just build that into our time, and have it all in. But at the same time, the next major effect that the Earth is feeling is that it's actually also bouncy, not just squishy. So there is the so-called post-glacial rebound. Um, a lot of places on the globe were covered with immensely thick amount of ice in the glacial period, which actually was so heavy that it deformed uh, Earth, and the Earth sank quite a bit, actually. And now those regions, mostly in the polar areas, are actually springing back to the original shape, right? And so that means that the Earth is getting taller and narrower. And as you have seen on the previous slide in the equations down at the right, if the radius is getting smaller, then actually the coefficient of inertia is getting smaller. And that means that the Earth is speeding up. So it's slowing down because of uh, the moon and the sun. It's speeding up because of the post-glacial rebound. So and it's doing that in a very complex way. Uh, Also, there is quite a bit of internal mechanics inside of Earth that actually make that even more complicated to calculate. So complicated that it is actually not possible to predict. Right. So the um, when the astronomers have been designing the atomic time, they decided, okay, we know that we can't keep our clock synchronized with the actual position of the Earth, then that would be a problem because we would not be able to find the stars that we are looking at the right places. So let's just introduce a correction. We have the leap year, which adds an extra day because the number of days or number of Earth rotations is not an exact multiple of the time that it takes for the Earth travel around the Sun. So we do the same thing. We just add a leap second. A leap second is an extra second in a minute, and yes, the clocks actually count to 23, 59, 60, and then start from 000 again on those days. And then it can happen basically on any last December or on any last June in a year, right? And it can go both ways. So the time can be adding an extra second, or it can be removing a second. In case the Earth would be speeding up, in case the glacial rebound would actually have a bigger effect than the moon and the sun. So far, that has not been the case. So far, we have only been adding seconds every couple of years. And the last event when that happened was in 2012. Well, actually, it happened since as well, but this one was the big event because it happened after a couple of years of no activity when the time was okay. The time is distributed on the internet using the NTP protocol, and this actually shows how the information that a leap second is coming was spreading through through the internet. And as you also can see, it actually takes a while for all of the NTP servers to be aware that the second is coming. It starts a month early, right? Actually on the 1st of June, and then on the last of June it actually happens. And if you look at some of the lines, you will see that some of them don't actually reach 100%. Right, so some of the servers actually did not notice, were improperly configured, and did not process the leap seconds. Right, so after that, their clocks were off by a second. Now, off by a second does not actually sound that bad, but well, in 2012 something even worse happened than just some clocks being off by a second, and that is there was a bug in the kernel in the handling of uh, clocks in the timer subsystem. So why actually the kernel needs to care about leap second? Well, because it needs to be displaying the clock correctly, but at the same time, the kernel internal clock is kept in seconds since boot time, right? So, and those two diverge if you add or remove leap seconds. So the kernel actually needs to keep track of all the leap seconds that happened so far and add it or subtract it depending on whether it wants to display the real time or the uptime. And that was a problem because, yeah, there was a function called clock was set, which actually updates those tables. And so internal timers in the kernel would get off out of sync every time a leap second happens. Well, that was what was a bug that was introduced in the kernel just before 2012. Actually, in an attempt to make this work right by the upstream. And well, what happened is that since all the internal timers were actually shorter by by 1 second, again, this doesn't sound too bad. So I mean, you have a timeout on a TCP packet, and it's supposed to take 2 minutes, and now it takes 111 seconds. Nobody notices. The problem is with timers that are 1 second or shorter, because now they are actually all taking 0 seconds. So if you have a software that is polling for an incoming packet, for example, every second, that doesn't create any particular load on the system. That is actually quite okay. And we know that, for example, COBOL or Java languages really like to do that. Then if that timer is reduced to 0, well, then it's pulling constantly and is hogging up all the CPU. And that is a problem. So actually any application that use timers less than a second to do constant polling would suddenly consume all the CPU in the machine. Particular applications are using a lot of threads. So the person that shall not be named that actually implemented this or has introduced this bug into the kernel noticed the rumor says they noticed that and actually did spend that day locked up in their basement because they were a little bit worried what this bug will cause in the world. The good thing is this is intentionally happening at midnight, such that the disruption is actually minimal. People are not doing all that much, and so that should really minimize the impact. The problem is that, yeah, that's a midnight in Greenwich. So there are some other countries where it actually um, arrives right in the middle of the day, and one of them is Australia. So yes, this kernel bug has actually activated in 2012 as a result of the leap second introduced by the International Astronomical Union. And all the systems that were running Linux, pretty much all of them, started exhibiting this behavior. And that has caused quite some grief across the world, not just limited to SUSE systems, of course. And for example, in Australia, it took down an airport ticketing system. So all the flights were delayed by the time it took the operators to contact SUSE, get that resolved, um, and get the systems running again, which was approximately half an hour. So yeah, that was quite an impact of a quite simple omission in the code. That's the story number one. And let's move to story number two. What a little speck of dust can do. So this is a story of a big international bank that again shall not be named because we value the privacy of our customers. That has set up a major data center, right? And all the storage subsystem was in a beautiful SAN storage area network fabric based on the latest generation of fiber channel. But actually, a little speck of dust got into one of the optical connectors where they were assembling it. And this is actually a photo of the core, or actually of the front of the optical connector. The dark ring that you can see is the cladding of the fiber. It's the fiber, and the tiny 9 micrometer bright spot in the very middle is actually the core of the fiber. That's where the single mode radiation from the laser is going through. On the right side, you can see an example of what a tiny speck of dust looks like when it is on the surface of that connector. And it basically can block out all the light. But that's not what happened. What happened was that it blocked just a little bit of the light. And this is the standard architecture that you will see almost everywhere in the world for a fully redundant SAN configuration. So you have multiple servers. In this picture, we only have two. You have typically two switches or two instances of fabric. Again, each can be built out of many switches. And then you have two storage systems, which again can be internally redundant. What happened is that that speck of dust was on the connection from server one to server to the switch one, right? And it actually was not large enough to fully disrupt that communication. It was just keeping the link, but not being able to pass data in one direction, because actually you do have a separate fiber for each direction. So server one was successfully sending commands to storage, in this case, storage one, but was actually not getting any responses back. Now, it would normally be the role of the firmware of the fiber channel card in server 1 to signal, okay, something is wrong with the link. Operating system would actually see that the link is down, automatically switch to the link to switch to, and everything would be operating normally. But the firmware, because the disruption was just marginal, did not detect link down and was still saying that that link is okay, despite actually no operation succeeding. So server 1 was dead at that time. Now the problem is server 1 was still sending requests to storage, and those requests were coming back, and switch 1 was not able to send them to server 1 because from its point of view that link was actually down. And fiber channel has one interesting property in that it doesn't expect, it just assumes, it just postulates that packets will never get lost. And if they do, that just creates I/O errors instead of, well, like with TCP causing retransmissions. So when storage 1 is sending the results of the request for server 1 to switch 1 because, well, actually it thinks everything is okay, switch 1's buffers overflow. And that means that it can't accept any more incoming packets because the buffers are full for of data for server 1, which it's not able to send there. Now, that is rather unfortunate because even when it receives any data for any other server from any other storage, now it actually drops the packet and causes I/O errors. So server 2 is also offline, as are all the other servers in the dataset. Yeah, and that's a problem, right? Because suddenly a major international bank is totally offline. And yes, this has caused a large number of unsuccessful transactions. And this story is just um, a reminder of how much error path testing is needed and important, although it's extremely hard to do. And so in the end, the switch firmware was updated as a result. The network card firmware was updated as a result to actually detect such situations. And neither of those were actually able to catch that. And then, well, we also added special logic to Linux to detect a situation where all the fabric says everything is fine, but it's not actually succeeding in delivering the data. And that resolved it. And yeah, another very, very stressful couple days that and we actually, yeah, debugged it all with the cooperation of those other vendors.
5 minutes.
Yeah, the last one is a short story, hopefully, and hopefully I'll find it into the 5 minutes, about a bug that was in the kernel for the longest time without anybody noticing. For that, we will need to take a peek at the Linux network stack, where there are actually two queues. One is the hardware queue of the network card, where you put packets on the network card and picks them from memory and sends them on the wire. And the other is the queuing discipline queue, which actually does smart things like putting more priority packets in the front for interactive use, uh, doing smart traffic shaping, traffic control, and so on. And this bug actually comes from the very simplest queuing discipline called P50 fast, which is called so because it's a FIFO and it's a packet FIFO and it's fast. Uh, so what happened is that some unnamed container slash cloud company that was trying to make it even faster. I added a patch into the Linux kernel with a lot of good explanation why it should be working. that made it lockless. So if for most cases, you would actually able to add a packet into the queuing discipline queue without acquiring a lock. And you can see that code right on the screen next to the cursor. It actually, instead of acquiring that lock, the sec lock, the QDIS sec lock, it just tries to do it. And if it does not succeed, it will just put the packet in anyway. And just hope for the best, basically. But yeah, the authors actually thought differently. They thought, well, this can never fail. But what this can do is that if a single packet is added from the queuing discipline into the driver queue, whilst at the same time the driver queue goes empty, then it will just be added to the queue, but the NIC will not be woken up to take care of it. Like the packet will not be lost; it will just be sitting there in the driver queue, and the NIC will think that the network card will think that the queue is actually empty, so it will not be sending that packet out. Now there is additional logic in the Linux kernel that actually says we will not be retransmitting any packets that are already in the queue because that would be counterproductive. We would then be creating duplicate packets. So the TCP stack will not even try to retransmit that packet. Now, under normal circumstances, any other packet will just fix that problem and wake up that queue. But a certain big cloud customer was actually having a special NIC just for storage traffic. And with storage, no packets are sent typically until the storage box responds. Now, what happens in this case is that that single packet is forgotten in the network card queue. The system is waiting for the storage to respond, but the storage never responds because it's still missing the last packet, and the whole system freezes. And yeah, that's worse if it happens in the cloud, because then it affects like hundreds or thousands of customers. Again, the solution was fairly simple: just fix the locking, and yeah, our engineers were able to do that quickly and get the customer back into production. And well, that's that. That's the end of the presentation.
Thank you, Vojtěch. I'm wondering if you have any questions. I see that in the chat there was some conversation regarding the 32-bit architectures and whether we are planning to support them going forward.
Let me take a look. Okay, 32-bit architecture and year 2038 problem. Yes, there are actually already existing upstream solutions for the 2038 problem. I don't recall exactly what's been proposed, but basically it requires breaking a little bit of backwards compatibility and just switching to a 64-bit number, even on a 32-bit architecture, because 32-bit architectures actually don't have any problem with calculating with 64-bit numbers. It just takes them 2 cycles instead of maybe 3. So that is absolutely okay. There is actually no problem having a fully working time on a 32-bit architecture. It's just that it will require some lifting in the applications because they are used to that field being a 32-bit. So the only problem where this will be is in support of legacy applications. Any new applications compiled against the new API will work just fine. And no, we are currently not expecting to support 32-bit application in SUSE Enterprise in year 2038. We still may be supporting some of them on OpenSUSE because, well, apparently people like running OpenSUSE in museums on their exhibits.